Hey QED coders, this is Michael. We're going to be doing a solo today. Jan is not going to be able to join us, but I've got an interesting topic that I wanted to talk about. So if you want to join us live, you can just go to immutablearchitecture.com and you'll get the link to the Discord. Come talk to us, hang out. And if you are joining us live on YouTube, then please leave a chat. I am trying to look over there and see them, but sometimes I miss them. So please let me know what you think. All right. So what I wanted to talk about today is a bug that my team at Improving, not the team that I'm actually working with, but a team, I still call them my team because they are using Janaga.net for a live application. They're using it for client work. And so I am a contributing member of that team because they're finding all my bugs and I'm fixing them. And they found a really good one that I started to fix last night, and then got to the point of diagnosing it and said, you know what, that is a good topic to cover. So let me turn on Visual Studio and I will show you the bug. So let's do a share just in case we've got anybody who's going to be joining us on Discord. And then we will bring up Visual Studio and see if I can get my picture over there. Okay, so this is the bug that that they ran into. In fact, I will start with the issue that they opened on GitHub. So we've got a model and a specification. They captured the specification in the generated language, the factual specification language, which is incredibly helpful. So thank you for doing that. So this is a common specification language that that Janaga.net and Janaga.js both produce and consume, and they do all of their thinking in terms of this language. So it's very useful to understand it. So when they run this specification in Janaga.net using the SQLite storage provider, they have an exception. Neither predecessor nor successor fact has been written, which makes absolutely no sense to anybody except for somebody who knows how the SQLite generator works. So this is one of those exceptions that I don't intend for the application developer to ever get. If there is a problem with the specification, I want them to get a readable description of that problem, and they should get that before it ever makes it to this stage. Once it is serialized as a factual specification, then it should be good. It should already be checked. So this is a valid specification, but it's not converting into SQL. We have to figure out why. And so to reproduce that, they gave me the model as you saw in the issue, and then I took that specification and turned that into some link that would produce exactly the same spec. But then I went one step further and removed the parts after I saw the error reproduce. I removed the extra parts that were not very important. So if you'll see here, we have a couple of negative existential conditions. So where not exists this successor saved or received. So as it turns out, this exception happens when you get to this part of the specification. It never makes it to the negative existential conditions. So I just removed those, ran it again, it still reproduced the error, and so we have a good test. Here I took a stab at what I think the SQL should be. And this is going to be important for us to talk through how this came about and what the solution is going to be. So if I run this, Control RT, then it brings up the build. It also shows us the Test Explorer. And let me go ahead and pin the Test Explorer so that we can keep looking at it. We've got our exception. Neither predecessor nor successor fact has been written. And this will take us right here into the SQL generator where we throw that exception after checking if the successor fact index is in the written fact indices or the predecessor fact index is in the written fact indices. Neither of those is true, therefore neither predecessor nor successor fact has been written. Makes perfect sense, right? Well, when you're looking at the code. So that is pretty much a marker exception. It means nothing when you're just looking at the text, but you can search for the text and you can find the code. And then it makes sense in context. But we want this exception to never happen. And I want to be able to prove that it never happens. That is pretty much the point of Janaka, is that it should generate provably correct behavior for anything that you can specify. So if you can write this and it passes some checks, then everything from that point forward should always work. SQL generation, inverses, feeds, all the things that we've talked about. So let's look a little bit more closely at this, and you can see that Zelda Freak here, his name is David Schwartz. You can see that David has a hypothesis here, that it has something to do with the fact that this specification takes 2 parameters, and this other one that he compared it with that works takes only 1 parameter. And his hypothesis is on the right track. There's one more, now two more steps beyond that lead to this defect. The next step is the fact that this unknown here has 2 path conditions. And we're going to talk about graphs quite a bit. And as we do so, we will see that if you have two givens, then you must always, at some point, find an unknown that has 2 path conditions. And that is a rule that is necessary in order for this graph to satisfy all the other conditions that I will mention soon. So 2 givens leads to 2 path conditions. So took that first step. The second step is that one of these path conditions takes multiple predecessor steps. So saved details and then details school. And as it turns out, it's important that it's the second one. So this is one thing that I found after I diagnosed this problem. If you were to take this and swap the order, so now the first one takes 2 predecessor steps, then it doesn't throw this exception anymore. It won't match this SQL, most likely. I haven't tried this yet, but if we get a failure, it's going to be because the SQL doesn't match. Yeah, failure, the SQL doesn't match. So it got past the exception and was able to generate some SQL, and this SQL probably is correct for that ordering. And so it's just the order in which it allocated F1, F2, F3, F4, etc. But even though that's a workaround, that's not what I want my team to have to do. I don't want anybody to have to tweak the specification in order to make it compile. It should always produce correct behavior given a correct specification. So, exactly what is happening here? Let's take a closer look at this specification. We can see that it takes those 2 parameters, session and school, And then it looks for orders of facts of type saved order. This one is taking one predecessor step session up to that session. And then this one is taking two predecessor steps, first to details, then to school, up to that school. Let's draw that out so that we can see that in a bit more detail. I have over here a lucid spark diagram. So I'm going to drop a couple of shapes. We've got our session. That is that one there. And we've got another one. That is our school. That is that given there. And then we've got this saved order. So, saved order is here. So you can see saved order has a predecessor relationship with session. So I can take this and I can just draw that line there. By the way, you might be a fan of Miro, you might be a fan of Mural, you might be a fan of Draw.io. I am a fan of Lucid, specifically for this this feature right here. Look at that. It always intersects, it always ends the line at the intersection of the edge and the line between the centers. That is the correct way to join shapes. These others use little handles off to the edges and on the corners, and you have to pick the right edge, and then it's never correctly lined up. But no. Intersection along the center. That's the correct solution. There is no other solution. Right, so. Oh, by the way, what happens if you do this? Yep. It does that mathematically precise thing, which doesn't quite make sense. Oh, that one's interesting. I don't know if that one's correct, but anyway. Okay. So we've got our saved order referring back to our session. Now notice we go back to saved and we've got details. So it's going up to details. So let's put another thing here called details. And we've got a line joining those. Okay, and then from details, we go to school. So, straight line, details to school. Now, this is the historical model. So here we are showing the arrows pointing up toward their predecessors. And that is showing how these facts are related to one another. So this produces a directed acyclic graph. You can see the directions in the arrows. There is another graph that is kind of laid on top of this that you can see if you just ignore the arrows, ignore the arrow tips, and instead look at this graph as if it were not directed. So you just have a graph. When you ignore the arrows, then because of the way that these graphs are constructed, you could actually end up with cycles. So I can't even call it an acyclic graph anymore. It's just a graph. That is the graph that the specification sees when it tries to execute. So let's talk about, oh wow, we've got a lot of colors. They've upped their game here. Lavender. Okay, so this is a given, and this is given. So we've got two places where we enter this graph, and this one down here, let's pick a different rows. There we go. This is an unknown. Okay, so if you take a look at the specification, we give a name to session and to school and to saved. So we have 3 facts that we've given names to. Those 3 facts are labels. So we've got a label here, label here, label here. Labels come in 2 flavors. The ones that we give names to up here are givens. The ones that we give names to down here are unknowns. And the reason for that should make a lot of sense if you think about how you were to execute this specification. You would be given a session and a school. You don't know all the saved orders. So you find those saved orders that match this particular graph. Given this session, given this school, find those saved orders. Which means that we have to execute the graph somehow from the fuchsia down into the rows, from the givens to the unknowns. So how exactly do we do that? When we are talking about SQLite, Postgres, anything that is backed by a relational database, we do that by generating SQL code. So this is SQL code that we generate inside of the SQLite store. So you can see we are saying we're going to say from a particular fact. We'll call this fact F1. So let me come up with some pistachio. I like that. Okay. Some aliases here. So we give the alias F1 to session. And then we find an edge. And this edge has the predecessor of F1, and it has a role that we can specify. And then we find F2, where F2 is the successor of E1. So that means that if we were to label this E1, then this would be F2. And so we continue our way around. We find E2, where F2 is the successor of E2. Notice here we did a predecessor join, but now here we're doing a successor join. So where this edge it has a successor of F2. Yep. And then its predecessor is F3. So we call that E2. So let's label this one. I'll try not to use the word label. I already used that word for something. It has the alias E2, and this one has the alias F3. And we continue up the ladder. So this is E3, and this is F4. So these are the aliases that we give to these edges, and these facts. And so now let's come back and take a look at how those labels, how those aliases connect to the labels. So F1 and F4 are the givens, and F2 is the unknown. So that's why up here, when I select the tuple, remember I'm interested in the tuples that represent the solutions to this this specification. F1 is the session, F2 is saved, and F4 is school. So F1, F2, F4. Those are the labeled facts. So I pulled those out. Those are part of the tuple. And then at the bottom here, I've got a where clause, and I say that I've got the fact type and the hash of F1 and F4, because those are the givens. F1 is session, F4 is school. Okay, so that is what we are trying to do. Go from specification into a SQL query that gives us this kind of a walk through the graph. And now notice when I took this walk, I didn't constrain myself to the directions of the arrows. Sometimes I went in the opposite direction, sometimes I went in the same direction. So I'm walking this graph, not the directed acyclic graph. Okay, so next we have a neat little constraint of the SQL language, and that is join. Now, it's possible to just say from all of these facts, all of these edges, and then have all of the joins happening in where clauses. That's possible. I'm going to ignore that. I suspect that the query generator will do the right thing with that, and it will come up with a nice efficient query that uses all the indexes. But by using the join keyword, I'm making sure of that myself. And that also means that I can have more control as I go from one SQL provider to another, that I can always use this syntax, and I know that it will produce the right thing. This way, by taking the walk in this direction, I can also always go to non-relational data stores as well, which might not have that capability of coming up with the query plan itself. So I'm basically creating a query plan by walking the graph and constraining myself by using the join on syntax. So the constraint when you're using join and on is that every join has at least one on. Makes sense? You can't just join and leave it open. I think actually there is a variant of join that does that, but I'm going to ignore that one as well. That's not cross join, but it's not inner, it's not outer, it's not cross join. There is another one that's just give me a Cartesian product. I really want a Cartesian product, but I don't want a Cartesian product. So let's try to always have an on. And so that means that this edge or factor that I bring in has to be related to something prior. And it doesn't have to be the immediate prior. In this case, it always is, but it has to be some alias specified previously. So that gives us a path that we can follow through the graph. If you were to generalize this a bit, sometimes this path could diverge. Maybe we have, I'll erase this after I'm done drawing the picture, but maybe we have something else that comes off in this direction. Let's make sure I'm not covering that up. I am covering that up. There we go. All right. Maybe we have something else that's coming off in this direction, and I want to include that within the graph. So that would have a label, so it's part of the tuple, and I want to walk that way and walk this way as well. So in order to accomplish that, I will be joining F3 to some future fact. Maybe this is F5, and then also joining it to F4. So it doesn't have to be strictly linear, but it does have to be fully connected, and each new alias that I introduce needs to connect to the previous subgraph. I'll say subgraph right now, because I'm sneaking up on the name of this data structure. The name of this subgraph is right there. It's a spanning tree. That's ultimately what we're trying to find. Find a spanning tree within this graph, this not directed graph, this not even acyclic graph. Find a spanning tree within it. So now there's some theory on spanning trees. If you did have cycles, so right here, this is not a cycle in the directed graph. This is still a directed acyclic graph, but this produces a cycle once you ignore the arrows. You ignore the directions. So the spanning tree is a tree. It does not have cycles, and it doesn't have, well, some trees do have directions. The spanning tree doesn't have directions. It's still not directed. And so now we are in a situation where we have two possible spanning trees. We can come through this direction, come back up, or we can come over here, and then go down that way and over that way, and it would fork. So a cycle just gives us more possible spanning trees. But here's one of those theorems in graph theory. If the graph is connected, then it has at least one spanning tree. That's an important theorem, and that's one that we will take advantage of. But in this case, we are looking at a situation where we just have these. These are the aliases that we're working with. So the spanning tree is all the edges that are in the graph in the first place. It walks all of them. It just has to walk them in a certain order. So now that we've got that theory under our belt, let's talk about why this particular specification gives us this error. So what it is going to do, and in fact we can see this a bit better if we go back to the factual specification. So we've got these two unknowns. We've got these two path conditions. Both of these path conditions are related to the same, these two givens. Two path conditions, both path conditions related to the same unknown. Use the right words. So the rule of factual is that a path condition belongs to an unknown. It's always inside of the braces of an unknown, and it starts with the unknown itself, and then it ends with something that's based on a prior label. So this being the first unknown, the only prior labels there are these givens. So that relates this unknown to a given. That relates this unknown to a given. And so that's the rule of how you have to construct these specifications. So because of that rule, okay, now there's another rule. Every unknown has to have at least one path condition. So those two rules are sufficient for you to prove that this, ignoring one condition or one possible circumstance with the unknowns, this specification produces a connected graph. So, well, okay, wait, I can't quite make that claim. So, coming back to this one, now I can make that claim. This specification has only one given, so therefore, by the rules of the specification, where every unknown has at least one path condition that relates it to a prior label, this must produce a connected graph. So, why is that? Well, because initially, my graph has just one fact in it, this one given. And then I introduce an unknown. So let's point at the graph here. We have just this one given. Then I introduce an unknown and an edge. The edge must connect it to some part of that prior graph. In this case, the prior graph just had one node in it. And so now this new unknown is connected to the rest of the graph. And so every time I introduce an unknown, I connect it to the rest of the graph. So that proves that if you have only one given, you have a connected graph. Now, two givens, it doesn't start connected. You have, why do I keep flipping to that one? This one here. You've got these two givens, these two things that I've labeled with the fuchsia. You've got these two givens, and they are not a connected graph. So then when you follow the rules of adding an unknown and relating it to one of the prior labels, now you've got a graph that has this little subgraph and that little subgraph, and those two things are not connected yet. And then you add this one So now that's part of this little 3-node graph with 2 edges. Not yet connected to that one. And then you add this one, and it says, okay, now it's connected. So because of that, you will always end up with, in order to achieve a connected graph, you will always end up with at least 2 path conditions inside of an unknown. If you only had 1 path condition in every unknown, then you would never connect these 2 givens together because they don't start out connected. So I have to connect to one and I have to connect to the other. So that is as an important thing to verify about each of the specifications. There is a situation in which I want to ignore some givens. If I were to produce a specification that never had anything that connected to school, then I would want to treat it as if that specification only had this one given. So if I didn't have this one, I would want to treat it as if that was just not a given, and that's the only thing that was provided. That situation comes up when we're talking about inverses. So that's not what happens today, for this bug, but that's an important part of the proof. So here we are with a specification that produces a connected graph, and I know that there exists a spanning tree within that graph, and yet my code is not finding that spanning tree. So how do we do that? How did that ever happen? So let's go back to the SQL generator. What are we doing right here? We're inside of generate joins. So we've got some list of edges, and then we've got a set of the fact indexes that have been written. And what I want to do is produce a join clause for each of the edges. So in the case that both the predecessor and the successor have already been written, so we've already got aliases for those facts, then I can just write a join edge on both the predecessor and the successor, filtering by role. So that one doesn't introduce any new fact aliases. These two, this one here is where you do have the predecessor but you don't have the successor. So now this is adding a join for the fact. So it is adding a fact alias, and it's adding an edge alias. So introduces an edge with the predecessor being that predecessor fact ID, and then a fact with the successor being that new fact ID. So add those two joins. Or if the opposite is true, the successor has already been written, then do the opposite. So you still introduce the edge and the fact. It's just, do you select the predecessor or successor fact ID? And so walking through these edges in the right order will produce those joins. But you have to walk through them in the right order. If you walk through them in the wrong order, then you will end up with some edge where neither the predecessor nor the successor has already been given an alias. So that could happen if you start with this edge right here, and you say, I want to join session to saved order. And then you immediately jump to this edge over here, E3. So now neither school nor details has been written. Why would that ever happen? Well, let's talk about how these edges are added to this data structure. So to show you that, let me set a breakpoint, debug this test, and we will get to the set of edges that we are trying to generate SQL for. So here we have, come on, you can do this. There we go. There we have edges. We have 3 edges, 0, 1, and 2. All right, so if we expand those, then we can see it's a bit small, but I'll make sure that this is in the thumbnail so you can see it a little bit bigger. You can see that the predecessor of the first one is 1 and the successor is 2. This is 1-based indexing. We wanted F1, F2, not F0, F1. I don't know why, but we are giving the predecessor an alias of F1 and the successor an alias of F2. So that is F1, F2. So this is the edge that we're talking about, these 2 things. Then we immediately jump to predecessor being 3 and successor being 4. So now we're talking about predecessor 3 and successor 4. It's actually the opposite aliases. So school is given F3 and details is given F4, but that's the edge that we're trying to write right now. So we're trying to write that as if it were E2. If you were to hold off a little bit, you would see that now here we're joining 4 to 2. So here we're joining details to saved order. So that would have been F4, and there's F2. So that's the edge that we're trying to join here. So if we were to walk these 3 edges in a different order, then we would produce a good spanning tree. So why are we walking these edges in this order? Well, that has to do with how we are producing the edges in the first place. So going back to here, and in fact you can see that fairly easily in the link. We say let's look for all facts of type saved order. So now we have labeled our unknown, and we are following our predecessors up from there until we hit session. And then we are following our predecessors up in a different direction until we hit school. So that means it's going to do this edge first, saved to session. And then it looks like it's going to do this one second, saved to details. Well, that would make a lot of sense, right? Saved to session and then saved to details. Sure, that would make a lot of sense. And then from details to school. That would be a great order in which to do things, but it's doing them in the opposite order. Why is it doing that? It's doing that because I know that we don't yet have saved. That can't be a starting place. We have to start from session or school because those are the givens. We have to start from a given, or at the very least, we can start from an unknown that we have already added to the graph. So we start here, or we start here. So the from clause of our SQL has to be one of these 2. And once we start there, then we can begin walking the graph. We can't start walking the graph from the middle. And unknowns are always in the middle of the graph. The givens are always at the edge of the graph. So, because of that, whenever we walk a series of predecessor steps like this, if those predecessor steps appear on the left-hand side, we reverse those. If they appear on the right-hand side, they're in the correct order. So if I had more predecessors here, I was doing session dot device ID, whatever. And then I was trying to join like that, for example. Not what we're trying to do in this case, but if I were, then starting with session, I would go up to device ID, and then from device ID, I would come back down to session, which includes the same one, but could also include additional ones, so you have to take both those steps. And then from session to saved, And that path gets you from session all the way to saved. And that's the direction in which you have to walk this. So, coming back here, in this case, you have to walk it from session down to saved, so it's still the same edge, but you're walking it in the opposite direction. You're walking this down the arrow. And then for this one, because we followed the same rules, we wanted to go from school down to saved. So we start here, go poop, and then we start here and go toop, toop, toop. So that means that was the first edge that we visited, and this was the second one. And then finally the third one. So here is the quick fix for this particular scenario. When you have one path join, or one path condition, then that logic makes perfect sense. You have a given, you don't yet have this unknown, so you have to walk from the given to the unknown. But then when you have the second one, now you do have the unknown. It's perfectly fine for you to walk in the opposite direction. And so in the case that the opposite direction leads you back to another given, then that will solve this problem. In the case that it leads you back to something that's already been specified, you'll just end up with a redundant edge, and you will end up in this place, where you're introducing a new edge between two facts that have already been added to the graph. So it's just an extra constraint on those on that graph. That one's not a problem. This one is the problem. So the first path condition, you walk in the direction of the right-hand side to the left-hand side, and every path condition thereafter for the same unknown, you walk left to right. And that will give you a nice path for your spanning tree that takes care of this particular issue. So, now that we've reasoned through all that, let's see if in the time remaining I can actually make that change. So, let's let the test continue. Yep, it throws. Good. We have our failing test. Okay. So how did I get here? Well, in fact, I probably should have just looked at the call stack to get there. Well, I already had the call stack in the exception. But here we've got the call stack. How we got here was this method right here, generate result SQL query, was given a query description, and this query description is where we have all those edges. So those edges are already in the wrong order inside of this query description. Okay, keep on going up. Okay, so here's the description.query description. So we are walking a result description, which is a tree, and producing a SQL query tree. So by the time this has been called, that's already been put in the wrong order. So keep on going, and right here, okay, the description builder.build. That gives us a result description, which has a query description, which has the edges in the wrong order. So that thing right there is what is causing all of the fuss. Okay, so we are inside of result description. Let's unpin that, give ourselves a lot of space so we can see this code. Okay, we've got some verification that we're doing here, and then we create the result description, so that's just right here. All right, along the way we're checking to see if the query description is satisfiable. That's a situation in which you're referencing fact types that you don't yet have in your database. So if those fact types don't exist, then that query is not satisfiable, and then you handle that accordingly. If that's inside of a negative existential condition, great, you just don't need to check that condition. But if it's positive existential condition or it's part of your joins, then the whole query is unsatisfiable. But that's not what we're dealing with today. What we are dealing with today is we've got, before we get to the compound projections, I skipped right over it right here, add edges. So I want to add all the edges to my specification, or to my result description. Okay, so we've got all of our matches. So a match is where you introduce an unknown and then it has a whole bunch of conditions with that unknown. So I gave that whole thing the name match. And so now you've got the path conditions inside of that match. You want to add those path conditions. Sort path conditions, that might be interesting here. So in that case where we had two path conditions inside of our match, so this one unknown introduced these two path conditions, we found that by flipping the order, we were able to make that work. And that's just because we put the longer one before the shorter one. That was the only reason that worked. So if we were to walk this from school to details to saved order, and then we walk session to saved order, because that second one only has one edge, we got lucky and it worked. But we can't rely upon that. So sorting the path conditions in order to fix this problem, not correct. Let's take a little side tangent and see if I can remember, why do we sort path conditions in the first place? Favor path conditions that reference known facts. Okay, I think that was just an optimization. Okay. I can't remember exactly why that ended up optimizing the SQL. But anyway, that's not the thing that's causing us trouble today. Here, when we add the path condition, that's what's causing us trouble. So here's add path condition. And we are doing a couple of things. So right here at the beginning, we're checking to see, so I know with a path condition that the label on the left is the unknown. So we don't even keep track of that label. The label on the right is going to be some other prior label. So do we already have a fact index allocated to that label on the right? If not, let's allocate one now. So that's that's not the part that's interesting right now. What is interesting is now that we've got the index for the label on the right, so that's a known fact, and so we get its index. Now we can start adding edges. So we're doing this walk in the same way for every single path condition. So no, remember, we're just inside of add path condition. We don't know how we got here. We don't know if this was the first time that we were called for this unknown, or if this was a subsequent path condition. In either case, we find ourselves here, and we are going through the roles on the right-hand side. So those are the ones that are after the equal sign. Let's save that and go back to the test. And you can see on the right-hand side, session, school, we have no additional roles here. When it had .device ID, now that is a role on the right, device ID. But in this case, we have no roles on the right. So, so this for loop doesn't do anything, and then we end up in this for loop where now we walk through the roles on the left. In that case, we do have some session here or details school here, and we walk through all those, and then when we are done, we reverse the walk to generate the successor joins. So here we have just added edges to an immutable list, and then here we are walking through those and flipping the direction. An edge knows the type of the predecessor and the successor. Actually, no, it just knows the type of the successor, and it knows the role ID. The role ID happens to capture the predecessor type, I think. Is that true? I might have that backwards. Anyway, the whole point is that we are going to reverse the walk so that we end up with edges that that start at the right-hand label, walk all of their predecessors, and then walk the successors down to the left-hand label backwards. So, in the case of, let's go back to this one. In the case of this one, we're going to start at school. We will walk any predecessor joins that it might have, so we might come up from here, and then we will walk back down until we get to saved order. In this case, since we didn't have any predecessors, we didn't leave this point, we just walked down. We just walked backwards. So, from school to saved order. From the prior label to the unknown. Which is usually the right way to do things, but if this is the second the second path condition, then it's actually exactly the wrong way to do things. We want to swap those edges. So, how can we do that? Well, I don't want to mess with this code, because this code is already doing all the right things. But when I call it here, if this is the first path condition, do things the way that that you need to do them. If it is the second path condition, then we want to return those edges in the opposite order. So this is the part that I hadn't really thought through. How exactly do I want to do that? Do I have time before I leave for work to get that done? The path condition, you'll see here, it is returning a new result description builder context. So this result description builder context, I'll show you what this is all about. This has got a whole bunch of immutable stuff in it. That should not be a surprise for this channel. So it's talking about a query description. That's the thing that we're trying to build, which is itself an immutable data structure. And then we've got this dictionary of the facts that the fact descriptions that we have talked about by their label, and then this this path, which is used for nested existential conditions. But we're not going to worry about that one right now. So what I really want to do is reverse the order of the edges that were just created in this query description. I think by this point here, that's already too late. We've already gone through all the effort of adding those edges. So let's come on back down here to the bottom. So after we have walked in the reverse order, or as we're walking in the reverse order, we can see that we're calling context with edge, and we are adding each of these edges to this context in order to produce the other one. Notice the other call to with edge happens not here while we're walking these predecessors, but here while we're walking these predecessors. So we are walking predecessors up the right-hand side, and we are adding those edges as we visit them. And then we walk the predecessors up the left-hand side, but then reverse them and add those edges in the reverse order. So I think what I actually need to do is put a condition around this to say which of the two do we reverse, the left-hand side or the right-hand side. So that means that this is going to be a bit more of a challenge than I can take on in the next 5 minutes. So, so how about tune in next week and we will fix this issue, and then we will have one step closer to a bug-free .NET runtime. So remember, the whole point is from a correct specification, I should produce correct behavior. Let's get one step closer to that. Will that be the end of the spanning tree journey? Will I be able to produce all spanning trees after this one change? Stay tuned. We'll talk about that too. So until then, build something awesome. See y'all later.